Hello, my name is Tim Grody, and I looked at optimizing circuit component placement. The goal of this project is to optimize the placement of components on circuit boards in order to minimize the difficulty of connecting them. Components are attached to circuit boards at small holes called pads, and these pads are connected to each other with traces, which are bits of metal that allow electricity to conduct between them. And the important thing is that these traces can't intersect with each other, or else you would have a short. This problem is important because even for experienced people, placing components can largely be a trial-by-error process. Poor placement will lead to issues with traces crossing over each other when you try and connect pads, and it can take a lot of time to get a good setup in order to not have any of these intersections. While automated part placement won't completely replace experts, it will help beginners find solutions much faster. Software already exists that is able to automatically place parts. However, it has a tendency to place objects in a grid and requires heavy constraints to work well and does not really consider the traces between components. Additionally, there are programs that can automatically draw traces and optimize circuit features, but they don't deal with the placement or moving components. Because of the difficulty of this problem, I decided to solve it using a genetic algorithm where the information encoded in the genome is the position and orientation of each component. The fitness function that I chose to determine the ease of drawing traces is the number of intersections between traces which are drawn as straight lines between connected pads. The reason that I chose this fitness function is that fewer intersections means fewer obstacles, which will mean that it will be easier to draw. For each generation, the genomes selected to breed were determined by a probability weighted by their relative fitness within the generation, meaning that a setup that did better has a higher chance of being picked to breed in the next generation. And children for each generation were made using a two-point crossover method. For the sake of simplification, each component was modeled as having two pads a fixed distance apart, such as what you would see for a resistor. Additionally, each component was represented in the genome by an x, y, and rotation part, where the rotation is an increment of 90 degrees. Additionally, for each circuit board being optimized, the area and connections between pads were fixed and fed into the program. Because this system exists in a grid, the search space is discrete. Additionally, on the left, you can see a sample schematic for how the results might look, where the red circles are pads and the lines between them are the traces. As you can see, this one has 0 intersections, which is a pretty good result. For a simple case, the program showed pretty good results. For a circuit that has 6 components and 8 connections in an 8x8 area, it took only 5 generations to find a case that only had 0 intersections, which took about 2.3 seconds of runtime. However, for a more complicated case with 24 components and 32 connections, it took 1.2 hours and about 1,200 generations for it to hit 0 intersections. However, it was also able to drop the number of intersections from just over 60 to 0 in that time, which is a pretty large improvement. Despite the success of this model in finding the 0 intersection case for the previous 2 problems, it has a few flaws. In reality, pads have a finite area around them that traces can't run through that isn't accounted for in this model. Additionally, the approach is entirely heuristic and not guaranteed to hit the global minimum. And for any given problem, it is impossible to know if the global minimum is 0, and the fitness function used cannot differentiate between these 0 intersection cases to determine which one is best. Additionally, the current model has a long runtime to produce good results for any system with a large number of components, and it only allows for a single type of component, which can be fixed upon in future iterations. Additionally, there is no consideration for the type of part, which may affect where you want to place them on the circuit board. In conclusion, this model provides a good starting point for placing components on a circuit board and can easily be improved upon to add in additional features in the future. Thank you.